welcome back. In the previous lecture, we had talked about the space of continuous functions. In this lecture, we are going to talk about the dense subsets of continuous functions. So let's start with one kind of simple density result. So if we need to approximate continuous functions by other class of functions, the natural candidate we have is all the polynomials are continuous functions. Okay, so in this lemma we are going to approximate the mod x function, and mod x function is a continuous function which is non-differentiable at a point. So in a sense we are going to approximate it by polynomials which are all continuous differentiable functions, and then it should converge to a continuous function which is not differentiable at a point. Okay, so it's like a model, it's like a prototype example, you can say. So the lemma says that we have a sequence of polynomials which converge uniformly to mod x in the interval -1 to 1. So to start with the proof, we take the constant polynomial 1 and call that as p0. Okay, basically it's you can think of this as degree p0. I mean the subscript denotes the degree of the polynomial that we have in this case. Okay, so we take a polynomial which is the constant polynomial 1 p0, and then using a recursive relation we define the other polynomials for n 0 1 2 so on. So it's pn plus 1, so n can start from 0. So p1 p2 everything is defined here. So p1 is defined in terms of p0. So for instance, when p0 is 1, you have here 2, you have here -1 squared, so 2 minus 1 is 1, so it's x squared plus 1 over half is a polynomial which is p1. Similarly, p2, you plug in p1 squared here, you get the polynomial p2 and so on. So we have a sequence of polynomials. Okay, and it's easy to, what we are doing is just multiplying and adding and subtracting polynomials. So right, so each of this is a polynomial here, and you can verify immediately that they satisfies this recursive relation, that is pn minus pn plus 1 is half pn square minus x square. This is the relation, this is the recursive relation satisfied by the definition that we have given for the n plus 1 polynomial. Okay, so this you can verify immediately. Just take pn plus 1, take pn, you subtract them, you can reduce it to this form. And we also observe this property that pn plus 1 minus mod x. So mod x is the function that we need to approximate using the polynomials. So pn plus 1 minus mod x can be written in this form, right? Pn plus 1 is this, so that is what we have here. I'm just multiplied and divided by 2 here, so that you can bring this inside the half here. So this can be simplified as 1 minus mod x square minus 1 minus pn square. Okay, that's the reason why we want to write it in this form. Anyway, we need to approximate this for all n. So we have defined a polynomial, we have these properties of this sequence that we have chosen. So now first thing we note is that mod x is less than or equal to p0. So mod x is defined in -1 1, right? So that interval, our domain was -1 1. So mod x is less than or equal to 1 there, and p0 is the polynomial that we have chosen. So mod x is less than or equal to p0, the constant polynomial 1. Now using this, we have that mod x is less than or equal to p1, which is less than or equal to p0. Okay, so this is coming from the previous property here, right? From here, so if I take n equal to 0, I have p1 minus mod px. Okay, so p1 minus mod px, here you will use p0. P0 is 1, so this becomes this, so 1 minus mod x square, and this we know is because mod x is mod x is less than or equal to 1. So 1 minus mod x square is anyway, mod x is positive, so 1 minus mod x square. So this is a positive quantity. So this is a positive quantity, which means that mod x is less than or equal to p1. Okay, and by the definition here, we see that p1 is less than p0. In fact, it's true for all pn's. Okay, so from the earlier property that we gave, we get this property and we get this property. So we have mod x less than or equal to p1 less than or equal to p0. Now arguing similar, so we did something for p0, now we obtained for p1. By induction you can actually obtain it for all n's. So mod x is less than or equal to pn plus 1 less than or equal to pn for all n. So what we have is, we have a decreasing sequence of functions which are bounded below by mod x, right? So decreasing sequence of real numbers. So once you fix an x, it's just a decreasing sequence of real numbers which are bounded below by the mod x. So it converges, and this happens for every x in this domain. So you call the limit of this sequence, the pointwise limit of this sequence, because it converges for every x. So define px as the pointwise limit of the sequence that we have chosen. Now by the recursive formula here, from here, now we know that Pn converges to P, Pn plus 1 converges to P, Pn converges to P, Pn square converges to P square, and so on. We have a recursive relation for P as well. So that is this. So we have a recursive relation for P as well. And from here, we actually obtain that P square is equal to x square. Okay, so the limit that we have defined here is actually, the square of that is x square. But this P is a limit of all positive sequences, right? All these polynomials were positive. Uh, all these elements of the polynomial were positive. So the limit is greater than or equal to 0, because it's a limit of a positive sequence. And P square is equal to x square, which means P of x has to be mod x, right? Px cannot take the negative. So you cannot have a negative x here, which takes for which x square max. So Px has to be mod x. And the convergence is uniform because the sequence that you chosen was a decreasing, right, monotonically decreasing sequence. And I think the previous lecture I had given you this exercise, that if you have a monotone sequence converging pointwise and so on, you can actually show that it's an uniform convergence, an exercise which I had given in the previous lecture, I believe. Okay. So this proves that we actually can obtain a sequence of polynomials which converge uniformly to mod x in -1, 1. Now we will extend this result more or less to in the entire set R, but now you cannot have a uniform convergence. It will be uniform convergence on compact sets, that topology, that compact open topology, right? And now we generalize it to not just mod x, and this you can do, right? Well, what we did in the previous lemma was when c was 0. So you can actually do this for any translation of that function. So mod x minus mod of x minus c. So you can actually find a sequence of polynomials which converge to mod x minus c uniformly on every compact subsets of R. Okay, so what is the proof of this? So the proof is that you take the sequence that we obtained in the previous lemma, just because we are going to call the new sequence that we are going to obtain in this lemma as P1, Pn. Whatever we called Pn in the previous lemma, let's call it Qn, right? So we have obtained a positive decreasing, monotonically decreasing polynomials which converges uniformly to mod x, right? Yeah, so let's call that Pn as Qn, that polynomial as Qn, right? So that tells you that because there is a uniform convergence for every epsilon, there is some number that bigger than that number, you have that the distance bit from the limit is less than epsilon, so you take epsilon to be 1 over k square, for instance, right? So you fix a k and take epsilon to 1 over k square. So corresponding to this epsilon, you have a n, and because of the uniform convergence, it is not going to depend on the choice of x. It's going to be valid for all x. So this this number nk depends only on this k here that we chose here. So we have this convergence, right? We have this estimate from the convergence of the sequence to mod x, uniform convergence of the sequence to mod x. So in this, so this is and this happens for all n bigger than or equal to nk. So in particular, it's valid for nk. So qnk minus mod x is less than 1 over k square for each k. So you call this qnk as the new polynomial. I mean, you just denote that q and k as the polynomial pk. We are just indexing it by k. That's it. So pk is q and k, and pk satisfies this. That is, pk minus mod x is less than 1 over k square, right? So for each k, if you do, you actually have constructed a sequence. You have actually picked a subsequence in a sense from the original sequence in minus 1 1, because the previous lemma was done in minus 1 1. We have a sequence such that Pnx minus mod x is less than 1 over n square, right? So with this property that we have picked that subsequence which has that it's strictly less than 1 over n square. Okay, so this capital Pn is that. Now using capital Pn, let's define the little pn. Little pn is defined as n pn x minus c over n, right? So little pn is capital Pn x minus c over n and multiplied by n outside. So now Pn minus x minus mod x minus c, that's what we need to show, that converges uniformly in every compact set. So Pnx minus mod x minus x, by this definition, use this definition here. If you use this definition here, you have Pnx minus over n, and then you multiply and divide by n here, bring that n out here, so you actually have this estimate, right? Whatever you have here. Pn x minus c over n mod x minus c over n. So here you have multiplied and divided by n. Whatever n you have there and whatever n that appears in front of Pn here comes out, and you have this estimate. And this, by the way we chose our capital Pn, is less than 1 over n square. So this is less than 1 over n square. With this n, it becomes less than 1 over n. Now this happens for all mod x minus c over n in minus 1 comma 1, which means mod x minus c belonging to minus n comma n, right? So mod x minus c belonging to minus n comma n, which means x belonging to c minus n comma c plus n, and this is a compact set in R. So right, and as you increase your n, you are going to, as your n is large, you are going to get as bigger a set. So for every you can cover any compact set by the choice of n here. Okay, so that proves this estimate. So what we have shown is that you can approximate the mod x function by polynomials, both in a compact set and in the entire set, or in R you can do it for every compact subset. Okay, so now let's look at the notion of separating points. You must have seen it in topology, the notion of Hausdorff space and so on, where points can be separated and so on. So in the space of continuous function, which again is a topological space, right? So depending on, we have seen it in the previous lecture, depending on whether the X is compact set or open set and so on. So if I take any subset A of the space of all continuous functions on X, okay, so when I write Cx here, I usually mean the real valued functions, real valued continuous functions with domain in X, right? That's what I mean. So we say a subset of Cx separates points of X if for any x comma y belonging to X such that X not equal to Y. So you choose 2 points which are not equal in X, then you can find an element in the subset A such that the value of f on these 2 points are also not same. Okay, which is what separate points mean. You take 2 distinct points, then you can find an element in the subset which takes distinct values on these distinct points. Okay, that's what separating point means. Now with this, let's look at a property of some subsets of Cx. So suppose A is a subset of Cx which has a following property. One, it is a vector subspace of Cx. Okay, it's a subspace. Every constant function, which is a continuous function, right? So every constant function is in A. Okay, so in fact, if you club it with the first point, you can say that's just the constant function 1 to be in A, because if 1 is in A by the subspace property, all the constant functions will be in A. Okay, so every constant function is in A, and then A separates points, the way definition that we have given here. If these three properties are satisfied by a subset of Cx, then given any two distinct points x and y, and any two real number a and b, you can choose a function f in the subset such that f takes the value a at x and b at y. So you choose two arbitrary real numbers and you choose two elements on the topological space X, then you can actually find a function which takes the decide value on a decide point. Okay, that's what this lemma tells you. So what is the proof of this? So we have assumed that the subset A separates points. So by definition of separation of points, there is a continuous function in G such that g of x. So suppose I take x and y. So here we have taken x and y distinct. So for given these two distinct points x and y, you can find a function g such that gx is not equal to gy, right, from the separation points. So that's what we are saying here. So there is a function g such that gx is equal to alpha and gy is equal to beta. So the alpha not equal to beta. Basically, gx is not equal to gy. So we're just calling that as alpha and beta. Okay, and they are not the same number. That's what separating point means. Now we are going to look for these constants s and t such that, and we are going to define f to be the dilation of G and translated by T. We are going to look look for a choice of S and T such that if we define F like this, it will, and then it satisfies whatever we require here. Okay, so